Alright, this third lesson is going to pick up where the second one left off. Similar idea here as to what we ended with yesterday. We can use our ideas of solving differential equations to determine population functions or height functions. The idea is we're taking this derivative, dp over dt, the derivative of population with respect to the derivative of time. We know it's modeled by this equation with an unknown constant, k times the square root of 2 plus 2, where k is an unknown constant and t is the number of hours of growth of a bacterial population. This problem is slightly different than the last one we did in that we are not told the initial population. If you're told the initial population, you have your c value and it's no big deal. But here we don't know it. So that's going to change things a little bit. But we're going to integrate this function, k times t to the 1/2 plus 2, with respect to time. And so when we integrate that, we get t, instead of 1/2, we add 1, so we get to the power of 3/2, which means we're going to multiply by 2/3, which is the same as dividing by 3/2. The k is still hanging out front, and we have plus 2t plus c. This is our p of t population function. But the problem is we don't know what c is, and we don't know what k is. We have two unknown values, but luckily we have 2 points. We know that after 3 hours, the size of the population is 270, and we know that after 7 hours, the size of the population is 537. And so now we need to plug in these two values into our equation separately, and we'll get a system of equations which we can then solve. So the population was 270 after 3 hours of growth. So let's plug in that 3. We'll have k times that 2/3 coefficient right there. Let's leave it 3 to the power of 3/2 right there, plugging in that time of 3. And then plus 2 times 3 plus c, and that is our equation. Now, we're going to be solving the system of equations. In my opinion, easiest way to do so is to use a matrix. So we're going to end up with a matrix that we want to look like this. We want to have a k column, we want to have a c column, and we want to have our equals column. And so we need to manipulate this equation real quick, because currently we have a k, we have some awkward number, and then we have our c. So we need to get that 2 times 3, that's 6, over to the other side. Let it join that awkward number over there, 270, so we're going to be subtracting 6 to do so. When we do that, the 270 is going to become 270 minus 6 is 264. So in my equals column, I'm going to have 264. In my k column, I'm going to have that entire ugly expression, 2 over 3 times 3 to the power of 3/2. You can simplify it, I don't care, but you can also just leave it like that. And then what's the coefficient on our c term? Well, it's just 1. So there's one of our equations, one row of our matrix, and now we need to plug in the other point. So we're going to get 537 equals k times 2/3 times 7 to the power of 3/2 plus 2 times 7 plus c. And we're going to do the same thing. We're going to subtract that 14 over here. That's going to give us 537 minus 14 is 523. And so our equation is going to look like this. We'll have the 523 in the equals slot right there. And then this will still have that 2/3. The only difference is that we have 7 to the power of 3/2 there. And then our coefficient on c is still 1. So enter this equation into your calculator. Type it in as a matrix, and then do the reduced row echelon form, RREF, and it will give you your answer matrix, 1, 0, 0, 1, and then it will tell you first your k value in the top row. Now, quick advice, when you're typing in those k terms, I would type it like this. I'd say 2 divided by 3 times whatever the value is, so in this case 3 to the power of parenthesis 3 over 2. If you type it in exactly like that, you will get the number you're looking for. That is as minimal as you could go. You could easily put parentheses around that part, and close that parenthesis off, and put parentheses around that whole thing if you wanted to, but you don't need any of that. And you should end up with your answer matrix that looks like this, 29.158-ish and 162.995-ish. And that's telling us that our C value, remember we have our K column and our C column, our C value is that number right there, 162.995. And with that, we're going to move on to position, velocity, and acceleration, because that is where we are headed next. Well, let's remember the connection. If you have a position function, like a height function, and you take the derivative of a height function, let's say d over dt right there, we're talking about time as the independent variable. So if we take the derivative of the height function, you get a velocity function. If you take the derivative of a velocity function, you get an acceleration function. But again, integration takes us the other way. If you integrate an acceleration function, you get a velocity function. If you integrate the velocity function, you get a height function or some sort of a position function. This is going to be useful information to us. Let's start with the observed constant of acceleration due to gravity on Earth, negative 9.8 meters per second squared. If we integrate that function, negative 9.8, with respect to time, we will get a velocity function. So when we do so, we get negative 9.8 t plus our constant c. But remember what the constant of integration represents in the context of a velocity function. It's going to represent your starting velocity, your initial velocity v0. And so we get this generic velocity function for free-falling bodies using the negative 9.8 force of gravity right there. And we get v of t equals that function. And if we integrate that function, we will get a height function. So we're integrating negative 9.8 t plus v0 with respect to time. When we do so, we will get negative 9.8 t squared. We'll divide by 2, which will give us a coefficient of negative 4.9 t squared, plus we v0, that's just a constant term, so when we integrate it, we get v0 t plus our constant of integration. But if we're talking about the constant of integration for a height function, we're talking about the starting height right there. And so this is our generic height equation that we've seen before, so this should be familiar. But again, keep in mind this is talking about meters as our units there. Now, that's our basic relationship there. We can differentiate to get down, and we can integrate to get back up. But we could take something like this. The acceleration due to gravity on the moon is a negative 1.6 meters per second squared. A pebble falls off a cliff on the moon. It hits the surface of the moon 15 seconds later. So we've got some cliff here. We've got some moon pebble falling down. Things we need to keep in mind is that if it is simply falling, or if you simply drop something, you're not throwing it up, you're not throwing it down, your starting velocity is going to be 0. Now, we don't know what our starting height is, but we do know that it ends on the surface of the moon. So let's call the surface of the moon 0. So we know that h of 15 equals 0, because it takes 15 seconds to get down there. That's telling us the point 15 seconds, 0 feet, right? T and meters right there. So we want to know how far it fell, so we need to know the starting height. If we know the starting height, we will know how far it fell. We also want to know how fast it's traveling when it hits. That's going to be the velocity. So let's integrate this acceleration function, negative 1.6, and we will get our velocity function, velocity function, v of t, equals negative 1.6 t plus our initial velocity, which is 0, so we just get negative 1.6 t. If we then integrate that was my attempt at drawing a tiny integration symbol. If we integrate that, we will get our height function, h of t, which will be negative 1.6 t squared divided by 2, so half of negative 1.6, negative 0.8 t squared, plus our initial height, h0. That will be our constant of integration there. And so, what do we know? Well, we know that the height is 0 after 15 seconds, so 0 equals negative 0.8 t squared, t is 15 squared, plus our initial height. So we can solve this equation for our initial height to determine that the initial height was 180 meters, just by plugging those numbers in. And then we want to know how fast it was traveling when it hit, so that's saying what is the velocity after 15 seconds, because we know it hit after 15 seconds. So we're just taking 15 and we're plugging it into our function for velocity, negative 1.6t. So negative 1.6 times 15, and you should get negative 24 meters per second. And you might be thinking, wait, why is it negative? In physics class, we're told you can't have a negative velocity. Well, we're not saying the speed is negative. We're just using that negative to identify the fact that the pebble was falling downwards rather than having been moving upwards. And there you have it.